Have you ever thought about like how hard it must be for animals to move around in places where there's like, you know, not a lot to hold on to?
Oh, yeah.
I was thinking about this the other day. Imagine scrambling over like a bunch of fallen trees in the woods, or even something simpler, just like walking through a construction site, where there are all these like gaps and stuff.
Oh.
And you have to find these little tiny places to put your feet. And somehow you have to like get from one to the next without falling.
Right. Yeah, you really start to appreciate it when you see it like that.
It makes you realize, like, wow, the animals that live in these kinds of environments all the time, like way up high in the trees, they're like seriously skilled at this, aren't they?
It is pretty amazing.
Yeah.
Like squirrels, for example.
Yeah.
They're constantly leaping between branches, often over what seem like huge gaps, and landing on these supports that are, barely wider than their paws. And what's really impressive, if you think about it, is how often they manage to land upright and keep their balance, even if they don't perfectly judge the distance or whatever.
It's true. They don't just fall out of the trees all the time.
No, they don't.
So that's what we're going to be looking at today.
Sounds good.
There's this really fascinating research paper. It's called Monopedal Robot Branch to Branch Leaping and Landing Inspired by Squirrel Balance Control.
Okay. Interesting title.
Yeah, and it goes deep into how squirrels are able to pull off these like almost acrobatic landings. And it's inspiring some really cool new ideas in robotics.
Oh, cool.
So today we're going to be talking about the secrets of how squirrels are so agile and then see how scientists are trying to build robots that can navigate like all these crazy complex environments just as well as a squirrel can.
So we've got biology and engineering both in the mix today.
Exactly.
I like it.
So basically, our goal for this deep dive is kind of twofold, right? First, we really want to understand what strategies these squirrels are using to like land so perfectly on these like ridiculously small branches.
Right, it's not just luck.
No, not at all. And then second, we want to see how researchers are taking what they're learning from squirrels, these biological insights, and using them to design better robots.
So taking inspiration from nature, biomimicry.
Exactly, because ultimately I think like this research could totally change the game for robotics,
Yeah.
If robots could move through all sorts of really difficult terrain, I mean, that could have huge implications for all kinds of things.
Absolutely. I'm excited to dig in.
Me too. So let's start with like the real stars of the show here, the squirrels.
Okay, good place to start.
What is it about like their bodies and the way they move that makes them so unbelievably good at navigating, these environments where there are just like branches and stuff everywhere?
Well, I mean, if you think about it from like a pure physics standpoint, leaping across a gap and landing on a tiny branch,
Yeah.
that's not easy.
Not at all.
You've got momentum to deal with.
Yeah.
You've got very little surface area to actually make contact with.
Yeah.
And there's not much room to use the kind of like rotational forces you'd normally rely on to correct your balance if you were on, a wider surface.
Yeah.
But as you said, squirrels nail these upright balance landings almost every single time,
Yeah.
even when their jump isn't perfect. So clearly they've got something figured out.
And what's even crazier is that they do all of this without having the kinds of things that help other tree-dwelling animals. Like, think of monkeys.
Yeah.
They've got those prehensile tails that they can wrap around things, right?
Like an extra limb almost.
Yeah, and they've got super grippy hands and feet, too. But squirrels, their grip strength, the paper actually calls it grasping torque, is pretty weak.
Interesting. So they're not just relying on, like, hanging on for dear life.
Exactly. There's more to it than that.
That makes sense. I mean, if you watch squirrels, they don't look like they're straining to hold on. They're so fluid.
Right, it's like they're barely even trying.
Yeah.
So this is what makes them so fascinating. It's not about raw strength or how tightly they can grip.
So what is it then?
Well, the paper points out this one key observation, and it's that squirrels actually change how much force and like twist they apply to the branch depending on how they're landing, like their speed, the angle of their jump, all that stuff.
So they're adapting in real time?
Yeah, it's super dynamic.
That's amazing.
Right. And this leads to the big question that the researchers are trying to figure out.
What's that?
What role do those forces from their legs, specifically the forces, like pushing towards or pulling away from the branch, they call this radial force, what role does that play in helping them stay balanced?
Okay, so it's not just about gripping the branch, it's about this whole back and forth of forces during the landing.
Exactly. And that brings us to the robotic side of things.
All right, let's talk robots.
Have you heard of Salto 1P?
Salto 1P. Rings a bell, but I'm not sure.
It's this really cool robot. Basically, it's designed to copy the way squirrels jump and land.
So like a one-legged jumping robot.
Yeah, exactly. Monopedal. And get this. It's super good at landing without falling over. It has a very high success rate, and this is all thanks to some really sophisticated balance control and, surprisingly simple gripper.
I'm intrigued. So how closely does it actually mimic the way squirrels land?
Well, here's the crazy part. The paper actually says that Salto 1P has even been able to land upright and balanced with almost zero grip torque.
Wow, seriously. So it's not just clinging on for dear life either.
No, it's not.
So it's really using those squirrel-inspired strategies.
Exactly. The researchers basically had this hypothesis, right? They thought that a big part of staying balanced comes from being able to control both the force and the length of the leg.
Okay, so by pushing towards or pulling away from the branch and adjusting leg length, they're changing the robot's center of mass relative to the contact point.
Yes. They basically thought that by doing this, Salto 1P could get much better at landing. And all of this can be done using the same powerful leg movements it already needed for jumping.
So it's kind of like a 2-for-1, using existing capabilities for a new function.
Exactly.
I like that. Efficient.
Right. So now let's talk a bit more about this radial force control idea.
Okay, let's break that down.
What exactly does radial force mean when we're talking about something landing on a branch?
So picture this. You've got the point where the robot or the squirrel touches the branch.
Right.
Right. And then you've got the overall center of mass of the, the squirrel or the robot.
Okay.
So radial force is the force that acts along that line connecting those 2 points. It can either pull that center of mass inwards towards the branch or push it outwards away from the branch.
So it's like an invisible line, almost like a tether that can pull in or push out?
Yeah, that's a good way to visualize it.
Okay, that makes sense. I guess, most people would instinctively think about rotation when it comes to balancing. If you start to tip over, you try to twist back upright.
Oh, absolutely. That's the natural instinct.
So how does this radial force idea compare to that more, intuitive approach of using torque?
You've hit on a really important point. And the research actually highlights some big advantages of using radial force for balance, especially when you're dealing with these really small footholds.
Okay, tell me more.
So first of all, radial force isn't really limited by how big or small the branch is. It doesn't matter if it's thick or super thin. You can still exert that force inwards or outwards along that line.
Right, that makes sense when you're talking about those really tiny branches that squirrels land on.
Absolutely. And then the second advantage, at least when you're talking about a robot like Salto, is that these robots already have to have really strong leg actuators to be able to jump in the first place.
Yeah.
To generate enough force to launch themselves into the air. So if they can use that same powerful system to control their balance during landing by adjusting radial force, well, that's pretty efficient from an engineering perspective.
Yeah, so instead of adding a whole bunch of extra stuff just for balance, they're finding a way to use what's already there in a smarter way.
Exactly. It's about working smarter, not harder, right?
Yeah.
And the paper actually mentions that a lot of robots that are designed for, hopping or running, they tend to separate their control systems. So, one system for movement and another for balance.
Okay.
And they often don't really consider how much this radial force could be helping them to stay upright. But this research really emphasizes how important it is, especially for landing.
So they're not just building robots and hoping for the best, right? They're also creating models to understand the physics behind all of this. How did they go about doing that?
Right. So they use simplified models, which is a common thing to do in both biomechanics and robotics, to capture those core physical principles without getting bogged down in all the little details, right? And one of the main models they used was something called an extensible pendulum model.
An extensible pendulum? What's that?
Well, imagine a basic pendulum, but the length of that rod that connects the pivot point to the swinging mass, imagine that can change.
Okay, I can picture that.
Yeah, so that's what they did. And this allowed them to represent those key movements of both squirrels and Salto during that crucial landing moment.
Got it. So in this simplified model, what were the most important things they were tracking to understand how the landings work?
So they focused on a few key parameters that basically describe where the lander is in space, its position and orientation.
Okay.
First, you have the tilt angle, which is just how far the squirrel or robot is leaning away from being perfectly upright vertical. And then you have the radial distance, which is the length of that pendulum we were talking about. So the distance from where they touch the branch to their center of gravity.
Okay.
And lastly, they have this thing called the body angle in the model. And this accounts for any spin the body might have as it lands. Like if the squirrel's rotating in the air before it hits the branch.
Oh, right, because that rotation would affect the landing too.
Exactly. So they
Well,
needed to account for that.
okay, so they're tracking the tilt, the distance to the center of gravity, and the spin.
Yep. And then they also needed a way to represent how much force or torque the squirrel or robot could use to control the landing.
Right, because they have to be able to adjust things to stay balanced.
Exactly. So they use these concepts of foothold torque, radial force, and body torque. And these represent how those imaginary joints in their model, the tilt, the extension of the pendulum, and the rotation of the body, are controlled.
Got it. So those are like the control knobs they can tweak in the simulation.
Exactly. And one really important thing they did in their modeling was to assume there's a limit to how much force or torque they can apply at any given time.
That makes sense, like muscles can only exert so much force.
Right. And motors in robots have limits too. So by putting this constraint in, they could compare how a natural system like a squirrel and an artificial system like a robot would control the landing with those real-world limitations.
That's a good point. It makes the model more realistic. So how did they actually define what counts as a successful landing in their model?
Well, a balanced landing in their model met two main criteria. First, the center of gravity of the lander had to end up directly above the foothold on the branch.
Okay, so basically they have to be centered over this support.
Right. And second, any rotation around that foothold had to stop completely.
Zero angular velocity.
Exactly. They also considered a situation where, if the lander could bring its center of gravity really close to the branch, almost like hugging it, that would also be considered balanced, even if the tilt wasn't perfect.
Oh, right, because sometimes you see squirrels kind of clinging to the branch like that.
Yeah, exactly.
Now, you mentioned something called effective torque earlier. What exactly is that, and how does it fit into all this modeling of forces and balance?
Yeah, so effective torque is a pretty clever concept they came up with.
Okay.
They realized that you can combine the effects of the torque applied at the foothold with any torque generated by the body's movement or posture into a single measure.
So instead of thinking about two separate torques, you can look at their combined effect on rotation.
Right. And this combined effective torque really helps to understand how you can control the twisting motion during landing.
Makes sense. It simplifies things a bit.
Yeah. And this effective torque basically influences the force that's acting perpendicular to that radial line we talked about earlier.
Okay.
And that perpendicular force is really what's controlling the overall rotation of the, squirrel or robot around the branch.
So it's like a domino effect. The effective torque influences the perpendicular force, which then affects the rotation.
It's exactly.
Okay, so they got these models, they know what to track, they understand effective torque. How did they actually test out different strategies for achieving a balanced landing?
So in their initial models, they used something called bang-bang control.
Bang, bang control. That sounds a bit aggressive.
Aha, it does, doesn't it?
Yeah.
But it's actually a pretty simple idea. Basically, they determine whether to push inwards or pull outwards with the radial force, and whether to twist clockwise or counterclockwise with the effective torque, based on whether the model predicts that the lander will swing too far over the branch or not far enough.
So it's like an all or nothing approach.
Yeah. And they use this variable called epsilon to represent how much the landing is expected to overshoot or undershoot the target.
So it's like a reactive system. If the model says, hey, you're going to swing too far, it immediately applies the maximum force or torque in the opposite direction to try and correct it.
Exactly. It's like flipping a switch. Exactly. And the cool thing is that when they looked at real squirrels landing, they saw similar patterns in how they were adjusting their forces and torques depending on the situation.
Oh, wow. So the model actually reflects what squirrels do in real life.
Yeah, it seems like squirrels might be using a similar kind of on-off control strategy naturally.
That's amazing. But I imagine translating that simple bang-bang strategy to an actual robot is a little more complicated, right?
You're absolutely right. In the real world, you have to deal with things like, mechanical limitations and delays. And Salto's leg, for example, it uses what's called a series elastic actuator, which is great for storing energy and making those powerful jumps.
Okay.
But it doesn't react as quickly when it comes to changing forces.
So directly commanding a bang-bang radial force might not work so well.
Yeah, it's a bit too abrupt for the hardware. So instead, they controlled the desired length of the leg.
I see. So instead of saying, apply this much force right now, they're telling the leg where it needs to be, and the springiness of the actuator sort of smooths out the force application.
Exactly. It's a more gradual and physically realistic way to control that push and pull.
That's clever. And how did they handle the rotational control for Salto? Was it also bang bang?
For rotation, Salto actually uses something called a reaction wheel, which is basically a spinning mass inside its body. So it's not quite like how a squirrel applies torque with its paws on the branch, but it achieves a similar effect.
So they're taking those core principles from the squirrel, but they're implementing them in a way that works for the robot.
Exactly. It's all about finding the best way to translate those biological insights into engineering solutions.
So all this modeling and theory is great, but how did Salto actually perform when they put it to the test with real jumps between branches?
Well, the experimental results were really encouraging. They did a total of 30 jump attempts, and Salto managed to catch the target branch in 25 of those.
Wow, that's like an 80% success rate.
A little over 80%, yeah. Which is pretty impressive for something this complex.
Absolutely. Especially for a robot with just one leg.
Right. And in 2 of those successful catches, Salto actually managed to land perfectly balanced on the branch.
That's amazing.
Yeah. And what's really important to note is that in one of those trials, they specifically focused on isolating the effect of that radial force control during the initial part of the landing before the reaction wheel kicked in for balance.
So they wanted to see if radial force control alone could help it stick the landing.
Exactly. And it did. So that was a pretty big validation of this whole approach.
So they've basically got a robot that's using a squirrel-inspired strategy to successfully land on a tiny branch.
Pretty cool, right?
Totally. And I remember reading that they also used a very simple gripper on Salto.
Yeah, they did. It was designed to be super lightweight and to minimize how much torque it applied to the branch.
So the gripper's main job wasn't to clamp down hard.
Not really. It was more about just catching the branch. It has this kind of inverted V shape that basically cradles the branch when it makes contact. And by designing it that way, they could really focus on how well the leg was controlling balance through radial force and the reaction wheel.
So it's not just about brute force gripping, it's about finesse and control.
Exactly.
Okay, so after they gathered all their data from the experiments and the models, they started to analyze under what conditions a balanced landing was even possible, right?
Yes. They introduced this concept of balanceable regions, which is really insightful.
Balanceable regions, what are those?
So a balanceable region is basically the range of initial conditions at the moment of landing, things like the angle of contact, how fast it's spinning, and its velocity towards or away from the branch, where it's still possible to recover and get into a stable, balanced position.
Okay, so it's like defining the margin of error, right? How much can the landing be off before it's impossible to recover? That makes sense. And they use their models to compare how big those balanceable regions were for different control strategies. Right?
Yeah, they looked at using only torque control, only radial force control, and then both together.
Interesting. So what did they find? What strategy had the biggest balanceable region?
Well, for their squirrel model, adding that radial force control made a huge difference.
Oh, wow, really?
Yeah, it increased the size of the balanceable region by something like 470% for certain landing angles compared to using just torque control.
That's a massive improvement.
It is. And this was especially true for landings where the squirrel had a lot of rotational momentum, which is when it's most likely to over-rotate and lose balance.
So that ability to push and pull with the leg is super important for correcting those more chaotic landings.
Absolutely. Now, for Salto's model, they found that using only radial force control didn't work quite as well as it did for the squirrel.
Okay, but was it still better than just torque control?
Well, when they combined the two, the torque control from the reaction wheel and the radial force control from the leg, they still got a much bigger balanceable region, about 230% larger than with just torque control alone.
So even though the robot isn't exactly like a squirrel, using both strategies together still made a huge difference.
Exactly. It shows the power of combining these different approaches.
Now, all these findings from the models are cool, but did they actually match up with what they saw in the real world?
Yeah, the agreement between the models and the real-world experiments was actually really good.
That's reassuring.
Definitely.
Yeah.
It gives us more confidence in their results. The balanceable region predicted by the squirrel model lined up really well with what researchers had observed in previous studies of real squirrels.
Oh, that's great.
And for Salto, the conditions during its successful landings fell within the balanceable region that was predicted by the model for radial force control. So there's a strong correlation there.
That's awesome. It sounds like this radial force control is really a key ingredient for landing safely on those narrow supports.
It really seems to be.
So if we had to summarize, like, the biggest takeaways from all this research, what would you say are the most crucial factors for sticking a balanced landing on a small branch, whether you're a squirrel or a robot?
All right, let's recap. So the researchers highlighted 4 key features. First, you need a powerful and accurate jump to even reach the branch in the first place.
Makes sense. Got to get there first.
Right. Second, it's easier to balance if you approach the branch at a shallower angle, more horizontally.
Okay.
Third, being able to bring your center of gravity close to the branch is really helpful. For the robot, that means having a short minimum leg length.
Gotcha.
And finally, as we've been talking about, using both torque control and radial force control is essential for maximizing your chances of landing safely.
So it's about more than just grabbing on tight. It's about controlling your body in a really precise way.
Exactly.
It sounds like there might be some trade-offs involved with optimizing all those features, though, right?
Yeah, for sure. Like, remember how we talked about Salto's leg being really good for powerful jumps, but not so quick at adjusting the radial force?
Oh.
So there's this balancing act between optimizing for the launch and optimizing for the landing. And squirrels, with their more complex and adaptable limbs, they probably have an advantage there.
Right, because they can adjust things more smoothly and precisely.
Exactly.
So what are some of the big questions that are still out there? What kind of future research do you think could build on this work?
Well, one thing they mentioned was that the actual impact of hitting the branch, like the collision itself, might play a bigger role in stability than we currently understand.
Oh, interesting.
And they also said that studying how other tree-dwelling animals, not just squirrels, handle these jumps could give us even more insights into different strategies that nature has come up with.
Yeah, that makes sense. There are probably a lot of different ways to solve this problem.
For sure. And on the robotics side, a big focus will be on designing new control systems and mechanisms that can react faster to adjust radial force and also reduce that minimum leg length we were talking about.
So basically making robots even better at mimicking what squirrels do naturally.
Exactly.
So the big takeaway from all of this is that sticking a difficult landing on a narrow branch is about way more than just holding on tight.
It really is.
It's this super elegant and dynamic process of controlling forces. And that push and pull, that radial force, it's just as important, if not more important, than that twisting motion, the torque.
Absolutely. It's about using both effectively.
And this is true for both squirrels and for those cool robots like Salto 1P.
Right. It's a universal principle for achieving stability on these kinds of challenging supports.
Yeah.
And the really mind-blowing thing is that this knowledge could have a huge impact on the future of robotics in all kinds of areas.
Oh, yeah, for sure.
Imagine robots that can easily move through disaster areas, or inspect infrastructure in places that are hard to reach, or even monitor the environment in really complex terrain, all thanks to understanding how a squirrel lands on a branch.
It's crazy to think about, right? How something so seemingly simple can be so incredibly complex and lead to such big breakthroughs.
Absolutely. It shows how much we can learn from nature.
Exactly. So as we wrap things up here, it really makes you wonder, what other seemingly simple things in nature are we overlooking?
Yeah. What other hidden complexities are waiting to be discovered?
Right. Like what other obvious solutions are we using that might actually be missing a key ingredient? Just like how radial force was overlooked for so long when it comes to balance.
A great question to think about.
Correct.
And it makes you appreciate how much more there is to learn from the natural world.
Exactly. So if any of you listening have had similar thoughts, if you've been inspired by nature in unexpected ways, we'd love to hear about it.